Thank you very much. So, and thank you everybody for coming for a talk with such an obscure title. So, this is joint work with Adam Burkhardt and Maris Ozels. And the plan for my talk is as follows. So first, I will set up the stage and give an overview of the concept and representation theory called mixture-while duality. And then I will be able to explain our three results. So the first result is a construction of a Gelfand-Tsetlin basis for partially transposed permutations. The second main technical result is a construction of a quantum circuit for mixture transform. And finally, I will be able to explain how we can apply those two results to a problem of finding efficient quantum circuit for pore-based teleportation. So, and before I start, I want to express acknowledgement to all of those people. So I had very useful discussions with all of them. Okay, so let's start with overview of mixture-while duality. So the main object of my talk is the algebra of partially transposed permutations. And so what is this? So the way I would like to introduce it is through the abstract algebra called Fold-Brouwer algebra. So the way to think about it is that imagine that you have a permutation on n plus m elements, which we diagrammatically draw like that. And then what we will do, we will take last time systems and we will flip them horizontally like that. And so then just imagine that we do such a procedure to all the permutations and then we take a linear span of those diagrams. So this defines this Fold-Brouwer algebra. And the multiplication in this algebra is simply defined by concatenating those diagrams. And if you obtain some loops in the process, then you just replace them by a factor of d. So this is an abstract algebra, but for the purposes of applications in quantum information, we should think about it as a matrix algebra. So we will consider tensor representation, which I'll denote by this map psi. So it will map these abstract diagrams to matrices on n plus m qubits. So for example, if you consider qubit case, then this kind of transposition corresponds to a swap matrix, and this kind of horizontal double arc diagram corresponds to a normalized projector onto maximally entangled state. And in general, if you want to compute a matrix element in that tensor representation of arbitrary diagram, then you do like in this example over here. Now this matrix algebra of partially transposed permutations defined formally is the image under this psi map of the Fold-Brouwer algebra. So, and let's also remember that this algebra A is generated by consecutive transpositions, which will be denoted by the sigma I. And there is a special generator of the contraction if you go across the wall. Okay, so now let's consider another map, phi, which maps a given unitary matrix which acts on a qubit to a bigger matrix which acts on our full Hilbert space of n plus m qubits, like that. And now this mixture-while duality is simply a statement that both actions phi and psi, they can be simultaneously block diagonalized by a unitary matrix, which is called a mixture transform. And the blocks in this diagonalization are labeled by, basically they came from the set of reducible representations of this partially transposed permutation matrix algebra, which will be denoted by this A hat. So the EREPs, reducible representations, are labeled by pairs of Young diagrams with some technical condition, but equivalently this pair can be thought of as a staircase. Like so, visually you can kind of combine these two Young diagrams into this staircase like that. And so this is generalization of the celebrated classic Schur-Weil duality. Yeah, this result reduces to it when you consider n equals 0 or m equals 0. So now, before I go and explain our main results, I want to ask two questions basically. So this side, or the unitary side, is essentially understood fully. So those matrices phi lambda in all the reducible representations are known, but this psi lambda matrices were not known, somehow, at least explicitly in the literature. And also, it was an open question how to actually construct efficiently this mixed Schur transform? So these are the two questions which we aim to answer. So let's go to the first question, namely how those psi lambda matrices will look like. And so this is the content of this part, which is called Gelfand-Tsetlin basis of partially transposed permutations. So what is a Gelfand-Tsetlin basis? So the Gelfand-Tsetlin basis is a very general Idean representation theory. So, and I want to formulate it abstractly as follows. So imagine that you have like a sequence of finite dimensional semi-simple algebras, which are embedded one into the other. And let's assume that it's multiplicity-free collection of algebras. What do I mean by this? I mean that if you take an irrep of a AK algebra and you restrict it to this subalgebra k-1, this restriction is decomposed into direct sum of different ak-1 irreducible representations. So if you have that condition, you can apply this restriction repeatedly up to the very beginning, where this A0 is just a trivial algebra, and in that way you will decompose your irreducible representation into direct sum of one-dimensional vector spaces, and this vector spaces constitute this Gelfand-Tsetlin basis. So it's kind of almost a canonical way to obtain a basis. And this basis is labeled by paths in so-called Bratelli diagram. So in a moment I will show how this Bratelli diagram will look like. But for those of you who know a bit of representation theory of symmetric group, the Gelfand-Tsetlin basis in that context is known as a Young-Yamanuchi basis, and the Bratelli diagram in that context is known as a Young graph or a Young lattice. And the Bratelli diagram for our algebra of partial transpositions, so will look something like that. So let's have a look at this algebra A 3,2 on Q-trits. Then basically the vertices in each level correspond to irreducible representations of a corresponding algebra. And then up to the level 3, you will kind of connect the vertices if a vertex is obtained from the previous one by adding a box to a left Young diagram. And after you cross the wall, the rule is kind of changes, and what you need to do, you need to either remove a box from the left diagram or add a box to a right diagram. And so you kind of go to the last level. Let's take a look at this vertex. So this vertex corresponds to some reducible representation of our algebra. And then the set of all paths from the root to this vertex will label a basis in this irreducible representation. And yeah, the number here just counts the number of such paths, or equivalently, it's a dimension of the irreducible representation. Okay, so, and our main result here is an explicit formula how those matrices psi lambda act on those paths T. And I don't want to explain in detail all these formulas, I just wanted to show you, to give you an idea that those formulas are not that difficult. Yeah, so we can write those formulas for each of the generators sigma I of our algebra of partially transposed permutations. So, and we can recover the original formulas of the Young-Yamanuchi basis if we restrict our attention to the case when n is 0 or m is 0. And just to give you some concrete visual way to see our result, so this is an example how those matrices of the generator look like for this particular case. So the rows of this table correspond to different reducible representations of this algebra, and the columns correspond to generators of our algebra. So you can see that those matrices are quite sparse and the entries are quite simple. So this answers our first question, how those matrices psi lambda in mixture while duality look like. Now, the second question, how you actually achieve those bases? What is how you can construct this mixed Schur transform? And so our second result is a explicit quantum circuit, which has linear complexity in n plus m and polynomial in d, gate and depth complexity. We have two different ways to encode the Gelfand-Tsetlin basis, and it leads to two different space complexities. Namely, in one encoding, you need to have n plus m times log n plus m auxiliary qubits to implement those transformation. And in the other encoding, you need just to have log n plus m qubits. So yeah, this encoding was not described in our original submission. This is the content of a future update of our paper. So, and the construction is based on the original idea for the standard Schur transform, which appeared in the work by Bacon, Cheung, and Harrow quite some time ago. And it's quite straightforward. And what we propose, we essentially propose to use the dual Clebsch-Gordon transforms to extend this normal Schur transform to this mixed version. I should also say that there is independent and simultaneous work by Quinn Nguyen, who is going to present the next talk. He describes the same construction in the standard encoding, and he proves actually the better upper bound for the complexity, so more explicit upper bound here. And again, just to give you an idea how this looks like, so this is our mixed Schur transform. If you open up this box, you will see a cascade of Clebsch-Gordon transforms. And so like this part of the circuit was the original Schur transform, which, so you see this plus signs over here. This is like a original Clebsch-Gordon transform. But once you go to the step bigger than n, you start to use this dual Clebsch-Gordon transforms over here. So this is like a first recursion in n plus m, but then you can go and open up the box how this Clebsch-Gordon transform look like, and you'll see another recursion, but that time this is recursion happens in the local dimension. Again, I don't want to explain in detail what these gates mean. I just want to give you a feeling how the circuits look like actually. Okay. So this answers our second question about this mixture-while duality. Now we have an efficient quantum circuit to go to this Gelfand-Tsetlin basis for partially transposed permutations. So let's try to find some problem to apply. And so the problem we choose is the problem of finding an efficient construction for the port-based teleportation protocol. Okay, so what is a port-based teleportation? So it was introduced by Shinzaka and Hiroshima in 2008. And schematically, it looks as follows. So Alice has a state psi which she wants to teleport to Bob, and Alice shares n kind of halves of the EPR pair, and Bob shares the other n halves. And what Alice does, she applies a complicated measurement, and what presumably should happen is that the state will be teleported to one of those n systems, and so those n systems are called ports. And yeah, and then what Bob needs to do is just to trace out kind of the rest of the system on which the state was not teleported. So kind of the characteristic feature of this protocol is that here, in contrast to the original in contrast to the original teleportation protocol, Bob does not need to apply a correction operation. Yeah, so this is very nice, and but it has, on the other hand, it has a cost. So you cannot actually implement it exactly and deterministically. And originally, it was presented as an example of a so-called approximate universal quantum processor, and there exists a well-known non-programming theory in which forbids the existence of exact universal quantum processors. So there were quite a lot of works in the area. So, and all those works resulted in the detailed analytical understanding of the port-based teleportation. So people were able to find expressions for the optimal measurements. You can also, instead of EPR states, you can choose some complicated optimized resource states. And yeah, essentially it was understood analytically, but it was not clear if all those expressions, if those expressions for PAVM can be actually implemented efficiently as a quantum circuit. And the representation theory of this partially transposed permutation algebra when m is equal to 1 is crucial to actually understand the protocol. And so our work answers this question in positive. So we provide inefficient circuits for those measurements. And so as you can see, we have like n square gate complexity, and in terms of depth or like time complexity, you can achieve linear and n scaling and n log n auxiliary qubit space complexity, or you can achieve like n square, but log n space complexity, n square time complexity and log n space complexity. And so this result about this so-called Yamanuchi encoding is presented in the follow-up paper which just appeared 1 month ago. So I want to briefly explain how our construction for those measurements work. So I should mention that usually people consider two types of pore-based teleportation protocols. One is a deterministic and one is a probabilistic. In deterministic pore-based teleportation, Alice always succeeds in measuring some outcome. In the probabilistic case, Alice has an option of aborting the protocol. And this option allows her to boost the entanglement fidelity. But in the deterministic protocol, because of the non-programming theorem, you cannot achieve perfect entanglement fidelity. And you can consider different resource states, as I mentioned. You can consider some more complicated optimized resource states. And from previous work, the measurements for all those cases were understood. And these yellow cells correspond to a very special measurement. It's a pretty good measurement. So for all those three cases, you need to run the pretty good measurement, which is defined via those formulas. So here you can see that these raw case states, you get them by conjugating the generator, contraction generator of partially transposed permutation algebra by cyclic shift operators on first n systems. So now we can use our Gelfand-Tsetlin basis understanding to rewrite those POVM elements in this basis, and further we can use it to dilate this POVM into a projective measurement on the larger Hilbert space. And so this is called the Nymark dilation. And I don't have time to explain in detail how that works, but again, the high-level idea is that in the original Hilbert space can be thought as a space of paths in the Bratelli diagram for our partially transposed permutation matrix algebra. And what we do, we will extend this Bratelli diagram in a very specific way. So we will add some vertices and we add some more paths to it. So it enlarges our Hilbert space. And in that Hilbert space, this is a Nymark dilated Hilbert space, we can construct a dilation of our POVM to a projective measurement, and projective measurement turns out to have the following form, where this UK unitaries and W unitaries are actually easy to implement unitaries. And in fact, actually, this UK unitary is this cyclic shift unitary to the power k. And the W unitary is also kind of easy to describe in the Gelfand-Tsetlin basis. And now it's kind of clear what we need to do. So what we need to do, we need to implement this unitary V, which you get from those orthogonal projectors by k. And it will have those eigenvalues which are roots of unity. And implementing this is easy. So you can remember this unnamed primitive from the Robin Katari tutorial. So here you see these phase gates which are applied, and and those unitaries and this U and W unitaries are actually easy to implement unitaries. It's kind of given to us. And implementing the power power of this unitary V is kind of trivial. You just put the I here in this phase gates. So you can now run the phase estimation circuit, and this will implement this Nymark dilated PVM. So in summary, our circuit will look something like that. So in the beginning, Alice will apply a mixture transform on her portion of the ports and the state which she wants to teleport over here. And then there will be like a sequence of those U unitaries with this W unitaries and phase gates in the middle, which are applied in the specific subspace defined by the projectors. Again, I should say that there is an independent and simultaneous work by Gianni Fei, Sidney Timmerman, and Patrick Hayden, which is also going to present going to be presented in the current session. And they describe a different approach, which is based on the block encoding techniques, and they constructed different circuits for that problem. So this brings me to my final slide. So I wanted to briefly mention that our follow-up paper, which just appeared 1 month ago, we describe a small modifications to this PGM circuit for this pretty good measurement. And with these modifications, we can implement essentially any POVM for other PBT protocols. We describe in detail the Manucci encoding, and we discuss also how to prepare the optimal states. Also, I should mention another recent relevant work by those people, and this work describes a qubit probabilistic PBT case. Again, we have some block encoding techniques. I wanted also to briefly mention that the port-based teleportation is related to celebrated problem of non-local quantum computation, and the paper by Alex May very nicely describes this. And our construction leads to new lower bounds of the complexity of implementing unitaries non-locally. And finally, I want to mention that our ideas are easily extendable to a multi-port-based teleportation. This is our work in progress. So with that, I want to thank you for your attention.
Yes, so please, if anybody has questions, there's a microphone there in the middle.
Thanks, Dimitri. For the circuit complexity results, is it conceivable to have polylog dependence on D? Or is that not?
Polylog dependence on D for the mixed Schur transform?
Yeah.
Oh, yes. I think it's like original paper by Aram Harrow has this remark, and so you can look at his thesis. He has like a remark where he says you can actually achieve polylog in D, but at the cost of increasing polynomial for n, essentially. Yeah. So it's I guess it's like a folklore understanding that it can be done, but it actually was never written precisely how you do it.
I see. And you also didn't write it, or it's maybe not relevant in your case?
Yeah. For our case, we were just interested in having polynomial dependence in n and d. Yeah. So we didn't need it basically. Yeah.
Okay. Thanks.
Yeah. Oh, actually, I wanted to add one more remark that actually for port-based teleportation, I think getting rid of making this into polylog independence on D, I think it's highly, I would, I don't think it's possible actually. But for mixed Schur transform, I think it's possible. Yeah. So.
I think a nice talk. As far as I understand correctly, your construction can be applied for any dimension, but if you restrict your local dimension to be qubit, then can you obtain a simple construction of this transformation, or?
So your question is, you mean for port-based teleportation?
No.
Or for mixed Schur transform?
Mixed Schur transform.
Yeah, for mixed Schur transform, if you consider the qubit case, I guess you can simplify, a lot of things. I haven't really looked in detail how it works out for qubits. Okay. But I guess you can do something special in that case. Yeah.
Okay, thank you.
Okay, thank you for the talk. I wanted to ask about the comparison to the usual teleportation scheme, which is also deterministic in the sense that even if you don't use the measurements in the beginning, you can always put them to the back. Then in each, let's say, if I want to teleport a qubit, right? Mm-hmm. Then I have 4 outcomes of the measurement of the Bell measurement, and I would have 2 extra qubits that are kind of telling me what unitaries I have to apply. But I don't even have to measure, I think. It's just applying the unitaries depending on the values of these qubits.
Yes.
So in that case, I need 2 more qubits. How many qubits would you need to do this port-based teleportation? Do you gain anything in terms of space? Do you understand my question?
Well, yeah, like you kind of want to, you don't want to do this kind of controlled on the classical outcome thing, right? But yeah, like Bob can choose not to trace out systems. So like this box means just he traces out all the systems, but you know, he can just keep them. So, and apply some, you know, some computation in parallel on all those ports. So
Yeah,
that will be the kind of alternative to what you are describing as the usual.
I understood that you have this Nymark dilation, so you basically put the POVMs that you want to apply into PVMs, right?
Yes.
And how many more qubits do you need in the end? How does it compare in terms of space? How many qubits do you need to
For implementing the POVM? Or
yes, for everything basically.
Yes, okay. For it's basically here. So like this is what I referred as a space complexity. This is how many auxiliary qubits you need to kind of just run the circuit which we described. So it has this additional auxiliary qubit count.
And is that better or worse than in the usual teleportation scheme?
Yeah, I guess it's worse. Yeah, I guess it will be worse.
Good.
But yeah, but this is like the cost you need to pay in order not to, have these corrections. Yeah.
Okay, so you don't need the unitary gates because of this thing. Okay, good. Thank you.
Any other questions? Yeah.
Thanks for the nice talk. I was wondering in your circuit construction for the mixture transform, whether the recursion structure is connected to the structure of the Bradley diagram.
Yes, so kind of one way to understand the Clebsch-Gordon transform is, so what the Clebsch-Gordon transform is doing is like you add a box essentially to the previous representation. So yeah, you can think about it as being a sequentially adding a box, and then you'll need to decompose the tensor product, and the Clebsch-Gordon does it for you. Yeah, kind of this recursion in D, it comes from the unitary group representation theory, and so these matrices here are known as reduced Wigner matrices. So it's like it's a very special situation for this specific Clebsch-Gordon, where you have a tensor product of some reducible representation of a unitary group with a box representation. And actually, in general, for arbitrary qubits, the Clebsch-Gordon for decomposing arbitrary tensor products is not known. And it's like a very special case when you add one box. Yeah.
Okay, thank you.
Okay. Is there any one final question? All right. If there are no more questions, let's thank the speaker again.